Okay, thanks. My name is Åsmund Bakketun, and I will present some work we have done on the land surface part of the AROME-Arctic modeling suite. So you should be quite familiar with the AROME-Arctic model by now, but to remind you, this is the domain shown in the red area here. And it aims to add value in the European Arctic over the IFS and the MEPS ensemble prediction system in Scandinavia, in Norway. So as we know, the Arctic or numerical weather prediction in the Arctic has several challenges, and one of them is something we observe in the northern part of Scandinavia with during spring when we have snow melt and snow melting during spring, which can lead to these temperature errors in our forecasts shown in this figure. This is from a simulation which is similar to the operational model, and we have mean errors on the map. So the blue colors indicate that the model is too cold for this period. It's a 3-week period. So the operational AROME-Arctic model, it uses a fairly simple land surface model. It represents the entire surface, snow, open land, and vegetation in one temperature. Or actually, we separate between the open land and the forest, so we have 2 temperatures, but it's still a mixture of vegetation and open land and snow. But there exists an alternative in the model system already, which we have tested here. It's a multi-layer soil with solving a diffusion equation for heat. We also use the explicit snow model, which is the 12-layer model. And we have activated for the forest part of the model a multi-energy balance scheme, which solves the interactions between the vegetation, snow, and the bare ground. So these are some results from verification in April, May, June 2020. We can, it's the solid lines, they show the mean errors versus the forecast lead time for the reference in black, and our setup in red and blue lines. And we immediately see that the cold bias is reduced in this period. And also the mean absolute errors in dashed lines are reduced for all lead times after the 3rd forecast hour. Here we see the mean errors on the map with the reference on the left, and the new setup on the middle figure, the diff figure. And we see that most of these blue, or many of the blue stations, are now faded white or slightly red, so that we have increased the model temperature during this period. This is a 3-week period where the snow melt is most intense, and there is not much snow left after this period. So it's a kind of crucial period during spring. And on the right here we have the histogram of the same dots shown in the map, where the triangles are the reference and the circles are the new system, and we have succeeded to shift the distribution to around 0 for the mean errors. And the red rectangle here, it indicates the -2 to -1 degree mean error stations, which are the most problematic in the reference. So to investigate why we have this improvement, we have plotted here the snow depth on the upper panels for the reference in orange and the diffusion scheme or the new setup in blue, and we see that there's a large difference in the snow depth during this period. And on the right, the figures include stations which also measures snow depth. And we see that the reference actually corresponds better with the observed snow depth, but it still has this cold bias. So we're not sure if this is the cause of the improvement, but yeah, something is going on here, and we also see that the errors in the reference is largest when the snow melt is most intense, and when it's completely removed in the new system. Yeah, so here I show the surface fluxes on the left figure, and you should note that on the green lines here, they show the sensible heat flux over open land, and it's increased in the new setup, which is the solid lines. The dashed lines are the reference in this figure, and also the latent heat flux over forest the latent heat flux in orange and blue. They have kind of switched magnitudes between the two models, between the open land and the forest. So this is a feature we see. In total, the new setup, it provides or produces bigger heat fluxes from the surface, which explains probably this enhanced 2 meter temperature as well. And here I also show the soil temperature profiles for the two models, or on the left it's the reference. It's not really a profile. It's the blue is the surface temperature, which is combined snow and vegetation, bare ground. And the red one is a relaxation temperature, which models something like a diurnal mean. On the right figure, we have the full or the upper meter of the diffusive soil scheme, showing much more detail in every layer. And also the red lines here are the 1 meter temperature, which is much slower varying than which is represented in the forest restore scheme. You can also note the difference between the forest and open land. The forest is shown in dashed lines here, and the forest temperature is much lower in the new system as well, because it's models the snow below the canopy, so it behaves quite differently over forest. Yeah, so to conclude, the new model system, it models more realistic variables, or similar to what we can observe during special observations, like snow or soil temperature profiles. And it's because of this multi-layer soil and snow, we are able to model also, or represent surface conditions forced by weather systems at different scales. It has a longer memory, and yeah, we saw the positive impact on temperature bias during this snow melting season, which is problematic in the operational system. There's a mismatch in the snow depth model results, but yeah, this can be explained by several things, but I suspect that the snow depth is not the full picture. The snow fraction cover is also important here, and how it's modeled in the forest. Yeah, and I should also note that this new setup, it has almost no soil data assimilation and no snow analysis, so it performs quite well with no correction from observations, as the reference here do. that's it. Thanks.
Any questions for Åsmund?
I'm not a modeler, so this is going to be a novice question here. In your bullet there, you say that the outputs, certain outputs are more suitable for comparison with observations. What makes them more suitable? What makes other measurements not suitable for comparison with observations? And what's the difference with assimilation? If you're assimilating something, doesn't that make it imply that it's comparable?
Well, you can go and measure the soil temperature at 1 meter if you want, and the model represents this quantity. I mean, it's easier to compare this with the real observations than some kind of temperature that is not really physical in the force restore scheme. You have this relaxation temperature, which is, it exists somehow, but it's not so easy to measure. And the depth probably varies from day to day or season to season.
I understand entirely. When we're talking about a land surface model, and right, we see the same thing with the GEOS model of NASA comparing with the SMAP soil moisture depth temperature. So that part I understand, but that's only in the land surface sort of situation. Are there variables in the atmosphere that are more less related to physical measurements?
I mean, the atmospheric model is the same. It receives the same information from the land surface model here. So it's not really different, I think, in this setup, as far as I see. Yeah. The fluxes should be better or more realistically based, but if it's possible to measure a difference, I'm not sure, or it's not easier to measure this directly. Yeah.
Do we have more questions?
When you talk about the cold bias during these snow melt conditions, what is like the prevalent atmospheric stratification that we saw there? Was like throughout the day, was like in the time, was it in the nighttime? So is it more like unstable or stable? That would be important, considering that we always couple the lowermost model level in our AROME-Arctic setup to the surface.
Yeah, so which case this was, or? Well, it's 3 weeks, so I guess it's different scenarios.
Yeah, for example, you saw the better response in the lower snow level, right? And if you think about it's a stable situation, it will always receive the heat flux from the lowest atmospheric level, right? And since you have the multi-layer setup, it responds quicker, right? So this response that you see might be a bit accelerated by this coupling that we have. So I would like to know if it was like stable or unstable, if there's like a clear tendency where you can see these cold bias forming.
Yeah, that's a good question. I haven't looked into this, but I see, I mean, this force restore has a very strong oscillation in the errors, which are during morning and afternoon or evening. So I'm not sure if this is probably an unstable case, or you have heating from the surface in the morning and cooling during night. I'm not sure. I guess I need to look more into this.
Okay, thanks very much.